I don't know. I aim for that. I love when my brain gets me momentum of things.
I know. It's good.
So we're not.
Okay. So you got assignment 1 last day. Assignment 1 is on simple interest, right? Assignment 2 is on compound interest. Again, just 2 questions. What you'll notice is that there's some where I ask you to use your calculator, right? So answer the question using the TVM, the time value money functions of your calculator. We won't be able to do those until next day, Tuesday. Okay. Yeah, because we almost get through it today, but then I had a technical glitch yesterday, so I'm gonna have to end it. We'll see how much time we have. If we have time, I'll go through it with you guys so you have it, but otherwise it'll just be on Tuesday. So written assignment 1 is on simple interest, right? And written assignment 2 is on compound interest. Assignment 1 is due on Tuesday, and assignment 2 is due on Thursday. Where'd you get off, Emily, giving us 2 assignments? I know, the nerve. But test 2 is coming up too, right? So what's test 2 on? Simple interest and compound interest. Surprise, surprise. So you'll be well practiced. Okay, so test 2 is on November 6th, I want to say, for you guys. Test 2. On simple and compound interest. Is on November 6th. So we'll finish chapter 5 on Tuesday, and then we'll have our review session where we go through the practice test on the Thursday, and then we'll have our test on Tuesday, right? Yeah. Have it over and done with before the long weekend. Nice. Okay. All right. So any questions about the assignments? No? Okay. Oh, I'll make a note here. You will be able to do question 1A and C after today, and 2A and B after today. So you will be able to do question 1A and C, and question 2A and B after today. 1B and 2C are the ones on your calculator, right? But after you've learned how to use your calculator, you'll be flying through those, okay, on Tuesday. Okay. So. Yeah, you just list all the entries for your calculator. Yeah, good. Yeah, if you already know how to use your calculator, then that's great. Just list your entries when you're done. Okay. So, what's this calculator business? Oh, you'll see, you'll see. I think you might even appreciate it later. I'll make you work a little bit hard for it first. Okay. So, let's do a quick review. So last day we finished chapter 4, simple interest. We finished simple interest. right? We looked at how do we calculate unknown payment amounts. Calculating unknown payment amounts. And we went through an example exactly, or not exactly like, but very much like question 2 on assignment 1. Right? So we went through an example just to see how it all works. Okay. And then we looked at changing interest rates. Right. So if the interest rate changes throughout our term, right, how do we deal with that in the simple interest scenario? Of course, we're going to look at how we deal with that with compound interest as well, but that's for next week. Okay. So then we started compound interest. And we looked at, well, we had to establish a lot of terminology, right? We said, okay, instead of finding time, right, we're going to look at the number of compoundings in a time frame, right? So instead of, or for compound interest problems, we need to find n, the number of compoundings, and I, the periodic interest rate. Before we can start a problem. I'll say start solving a problem. Right? So we looked at, okay, well, n is the time times the frequency, right? Where t is time in years. Right, we've been dealing with t already, right? So we know how to convert it to years, all that fun stuff, right? And then, and f is the compounding frequency. And so we looked at some common compounding frequencies, right? The compounding frequency is just going to be how many times per year are we compounding, right? So monthly, that's 12 times per year, weekly, 52 times per year, bi-weekly, 26 times per year, right? So we need to know those. And we went through a list and just listing those common frequencies. Okay. So, and then we had I, the periodic interest rate, is R over F, right? Where R is the nominal, right, or annual interest rate. Mm-hmm. So then we established the formula. The future value is the present value times 1 plus I to the power of n. Right, so here we're not using R and T anymore, right? We're using I and N. And that's the difference really between compound interest and simple interest. And then we solved for the present value. We've been calling it for simple interest, right? We've been just using P. P is the present value. I really don't know why it's different for simple interest on the formula sheet for compound interest and simple interest, but it is. I'm sure there's a reason. I just don't know what it is. Find it confusing. Yeah. So in simple interest, right, we've just been using P. In compound interest, we use PV for the present value, but they're the same. So the present value for PV is the present value, which is P, which is the principal. All right, so don't be confused. Just remember that, okay, for simple interest, we use P, and for compound interest, we use PV. They're the same. Okay. So then we solved for the present value. That wasn't too hard, right? We had to just divide both sides by 1 plus I to the power of n. And we solved for PV, which is the future value, over 1 plus I to the power of n. Okay. You might think it's nice that the formulas are all given to you, right? They're already solved for compound interest, which means you can just use them right away, right? You don't have to derive them anymore, okay? But as the story goes in this textbook, today we're gonna derive I and n, right? Look at how do we find I, how do we find n, and examples dealing with both of those. And then a big problem, then we'll be done. Okay. So, section 5.3. Oh, any questions before we get started? No? 5.3. Calculating the periodic interest rate I and the number of compounding periods. Okay, so first we'll look at solving for I. So from the future value, we have the present value times 1 plus I to the power of n. We want to solve for I. So we know we have to divide both sides by the present value, so we have the future value over the present value is 1 plus I to the power of n. We need to shake that nth power, so we need to take the nth root of both sides. So we take the nth root like this, right? We put a little n in the hook. Future value over the present value is 1 plus I. And then we have to subtract 1 from both sides. So we get I is the nth root of the future value over the present value, all minus 1. We did it. If you look at the formula sheet, that's exactly what's on your formula sheet for I, right? So that's nice, but now you know where it came from. You don't necessarily need to know how to find it, but it might be good to know. I don't know. Or fun to know, I should say. Okay. So let's look at a problem where we have to solve for I, right? Usually though, we'll want to solve for the rate, right? What's the interest rate that made this happen, right? Made this amount grow to this amount in this amount of time, right? And so finding I is really just a gateway to finding R, right? Because first we have to solve for I, and then when we know I, we can use I equals R over F to solve for R. Okay? So we usually want to solve for the nominal rate R oops. First step is going to be solve for I. The second step is going to be to use I equals R over F to solve for R. Right? So now it becomes this two-step process. Just like if we're doing compound interest problems and we're given R, right? The first thing we're going to do is find I, right? Convert it to I. So now if we have to find R, we have to first find I and then we can find R. Okay? So let's do an example. Example 178. Oops. $15,000 was invested for 13 years until it reached a value of $30,000. If interest is compounded monthly, what was the nominal rate of interest? Right? So some amount grows to another amount, and interest is being compounded monthly in this case, right? What was the nominal rate of interest? Even though we don't need a timeline for this, right? I'm still gonna draw one just to get in the habit of doing them, right? And remember, the assignments are really just so I can mark you really hard on your timelines and mark you really hard on your work. But the timelines are gonna be where you're gonna lose marks, I can tell you that right now. But if I mark you really hard on the assignments aren't worth that much, right? And then you'll be really good for the test, right? So that's the method to my madness there. Okay. And it's only 2 questions per assignments. Okay, so let's do a little timeline here. We're only dealing with 2 time points, right? Let's say I invest 15,000 today, and 13 years later, it's reached a value of 30,000. Right. So put the time points up above and the amounts down below. 15,000, I'm going to show it grew to 30,000. Okay. On the arrow, right, we put N now for compound interest. N is time times the frequency from your formula sheet, right? Time in this case is 13 years times F, which is 12, which I think is 156. So we have 156 compoundings. And we want to find R. All right. So step 1 is find I. We can just go ahead and use the formula right away, right? Because it's on our formula sheet. So I is the nth root of the future value over the present value, all minus 1. So in our case, we need the 156th root of 30,000 divided by 15,000 minus 1. Funny you should ask. 156th root of 2 minus 1. On your calculator, remember how we did this? We have on your screen, you have 2, right? And then hit the y to the x button, because you want to do 2 to the power of 1 over 156, right? So do 2 to the power of 1 over 156. That's how we get the 156th root of something. Yeah, it's not very clear here. So I'm going to throw brackets around here. 1 divided by 156 is one button. So I have 2 to the power of bracket 1 divided by 156 end bracket. I get 1.004453137. Make sure you get the same thing. Okay. So this becomes 1.004453137 minus 1. Do not forget that minus 1. It's a pretty common mistake, right? Because we've done all this work and then, oh, minus 1, who cares, right? But 1.004, that would be 100%, more than 100% per period. That would be crazy, right? So it's going to be a really, really small number. Yeah. So then this becomes 0.004453137. So then step 2, now you have I. Step 2 is to find R. Right. You know I is R over F. So I, we said, was 0.004453137 is R, which we're trying to solve for, over F. I'll just jot down F up here. F is 12, right? We're compounding monthly. So now R is going to be 12 times 0.004453137. So minus 1 times 12. I have R is 0.053437644. Therefore, R is approximately 5.34%. Nice. Any questions about that one?
So I is the nominal interest.
R is the nominal interest rate. Mm-hmm.
So that's what you're paying for the interest per year.
Yeah. Yeah. All right. What if we have to solve for n? N is the gateway to t, right? So usually I'll ask you, how long does it take for something to grow from this to this if interest is this at a compounding of this? Fill in all the blanks, right? So how long does it take, right? We have to solve for t, but in doing that, we have to solve for n first for compound interest, right? So solving for n, from our formula, right, we have the future value is the present value times 1 plus I to the power of n. We've got n in the power. We know how to deal with that though. Remember logs, Right? We looked at all the log laws. We use logs to bring the power down. Right? But first we have to divide both sides by the present value. So we have the future value over the present value is 1 plus I to the power of n. Now I can take the log of both sides. We use the natural log. The log of the future value over the present value is equal to the log of 1 plus I to the power of n. By log laws, we can bring that n down in front, right? They'll be equivalent. So n is the log, or n times the log of 1 plus I. And I'll just make a note here. By log laws, which we established earlier in chapter 4. So now I'll just rewrite log of future value over the present value, stays the same. Now we can solve for n, right, by dividing both sides by the log of 1 plus I. So we have n is the log of the future value over the present value, squeezing it onto one line, I guess, over the log of 1 plus I, ta-da, is exactly what's on your formula sheet, right? So you have it, you can use it already, right? But it's good to know where things came from. So if you wanted to, and I kind of like the fewer formulas, the better for me. That's just how I am. So if I had my own formula sheet, I would just say, okay, well, I only need the future value, and then I can ignore all of these because I know how to solve for all of these, right, if I ever needed them, right? So that's just how I am, but they're on here, so they're all yours, but you don't actually need the present value I and n, right? You can solve for them. So same scenario, right? N is the gateway to finding t, right? So we usually want to find time. We usually want to solve for t, right? So step 1 is going to be solve for n. Step 2 is going to be to use n as time times the frequency to solve for t. So let's do an example. Example 179. In order to save for college, we can all relate. You want to invest $10,000 and have it grow to $15,000. Enough? Probably not. If the rate of interest is 8% compounded semi-annually, how long will it take for this to occur, right? So here we have some amount, we want it to grow to some other amount. We know the interest rate and we want to know how long is this going to take, right? Let's do a timeline. We don't need one for this, but I mean, I'm going to keep doing them even if we don't need them. It's good to see lots of timelines. On the test, remember, if you need to show a timeline, I will just tell you, include a timeline, right? Or I might do as I've done on the assignments, right? Where part A is do the timeline, part B is solve the problem, right? Just to force you to do the timeline. Okay? So if it's important, I'll make you do it. If you don't have to, then Who cares? So let's say she's investing this money today, and we want to know, we don't know how long it's going to take. That's the whole point of this problem, right? When is later? Right? I'll indicate t equals question mark, right? That's what we want to solve. I'll just jot down here that the rate, right, is 0.08, and the frequency is semi-annually, so twice per year. Okay. Just so I have them ready. Okay. So we want to invest $10,000 and have it grow to $15,000. On the arrow, we put n. We don't know n, right? Because we don't know time. That's what we're trying to find. So we can just say n equals question mark. Right? But just to remind ourselves that, okay, we need to find n in order to find t. And we're going to solve for I just anywhere below here. I is r over f, which is 0.08 over 2. So, oops, I is 0.04. That one's an easy one to forget in the beginning, right? Calculating I, we're so used to just using R. And even when I went through and I checked out assignment 2, I just go through them quickly and make sure they all work. I used R. And then I had to redo everything. But it's okay. So that's why I'm telling you, I'm not immune to this stuff. I'm just so used to using R. So we have to get in the habit of calculating I and then using I. Okay, okay, so step 1, we have to find n. N from our formula sheet was the log of the future value over the present value over the log of 1 plus I. It's going to be the log of 15,000 divided by 10,000 over the log of 1 plus 0.04. This is going to simplify to the log of 1.5 over the log of 1.04. Do you guys remember how to find logs on your calculator? So on calculator, right, you're going to have 1.5 and then hit the LN button. And then equals. So 1.5, oops, ln. I get 0.405465108. Make sure you get the same thing. So this I get 0.405465108. Last day we learned how to store these long values on our calculator, right? So I'm going to store this in 1. So you're just going to hit the store. So whatever you have on your screen is what you're going to store. So store in slot number 1. Right? You can pick any of the values, but I do recommend that you write down where you're storing things, right? So you can refer to it later. And then I can solve for 1.04, take the log of it, bless you. I get 0.039220713. Sure. I like to store stuff. even if I don't need it, right? If it's a long decimal, I'm just gonna store it. So then to solve for this, right, I'm gonna go recall 1 divided by recall 2. I get 10.33803507. Did you store it in 1? So if you hit recall 1, what does it show? Oh, maybe not. Okay. So n is 10.338 whatever compoundings. Okay. If we take it back to here, right, so now we know that n to get to exactly 15,000 has to be 10.3 whatever, right? And so this, the length of this arrow is exactly 10.3. We can't have 0.3 of a compounding, right? And if we only went to 10, we would be just a little bit short of 15,000, right? So for n, we always have to round up. So even though we're going to have a little bit more than the 15,000, that's better than not having enough, right? So we're going to take it from 10.33 to 11 compoundings. Exactly. So since we can't have 0.33803,507 of a compounding, we need to round up to the nearest whole number. So n must be 11, right? 11 full compoundings. I'll just emphasize that in a note, right? Whenever we've solved for n, we always have to round up to the nearest whole number. I do. Yeah. Whenever we solve for n, we need to always round up to the nearest whole number. Step 2, now we can find t. N is time times the frequency. If n is 11, nearest whole. But we have to round up. If Gerline, are you there? You have to round up. So even though 10 is the closest whole number, 11 is the closest one rounding up. So 11 is t times f. What was our f? I think it was 2, right? Compounded semi-annually. Nice. So then t is 11 divided by 2. T is 5.5 years. Just to be here, absorbing all this knowledge. Oh, the irony. So it would take 5.5 years. Any questions about that one? Nice. Nah. Because you indicated that you had to solve for it, right? So yeah, once you've solved for it, you're done. We can have fractions of years, right? And you don't have to convert it to 5 years and 6 months. So that's just way too much work. 5.5 years is fine. Okay. No questions, huh? So I'll just indicate that's the end of this problem. These problems all run into each other, that's why. Has anyone heard of the rule of 72? Sometimes you guys have, sometimes you haven't. So the rule of 72 is just to figure out approximate doubling time. Okay. So let's say you're at the bank and they tell you, oh, we'll give you a rate of 3%, right? So if you want to know how long something, so any value is going to take to double, you do 72 divided by the rate. And that just gives you a rough idea of how long it's going to take something to double, right? So why 72 has to do with logs and things, but yeah, huh? Years, yeah. So, yeah. So whether it be $1 or $1,000 or exactly. Nice. So, just a quick note on doubling time. Doubling time also works for anything that has a rate, right? So population growth, money growth, whatever. Bacterial growth, disease spread, morbid stuff. Rule of 72. Let's stick to money. So to approximate, right, this is just a quick approximation, right? So to approximate how long any amount will take to double, we can use the rule of 72, which says that the doubling time in years is roughly equal to 72 divided by the percent annual rate. Meaning that you use just the rate as it's given. So if I tell you, well, it's 8%, you would use 8, right? 3%, you would use 3. Or we can rewrite this as 72 over the R as a percent. So just grabbing a quick example here, example 181. What's fun is that it's for any amount. What's going on here? Hello. Oh, there it is. So even though we have an amount in this example, we don't actually need it, right? So an investment of $15,000 needs to double. At a rate of 8% per year, roughly how long will it take? Right, so this question we could have asked, at a rate of 8% per year, roughly how long will it take for an investment to double, right? So we don't actually need this one. Right, it's kind of unnecessary. Okay. So then we know that the doubling time is roughly 72 over 8. So it would take roughly 72 divided by 8, 9 years.
you don't convert it into the decimal.
No, I know. I've been always convert to decimals, always convert to decimals. And then here, no, we don't. So that's the tricky part. Right. Yeah, so 72 divided by 0.08. Try it, 900 years. You would probably say no thanks. Right, but this is kind of a quick and easy tool to use. Let's say you're at the bank and they're saying, oh, okay, well, we'll give you this rate. And then if you want to decide if that's good or not, right, you can look at the doubling time, and then that gives us kind of an idea of, okay, well, am I okay to wait that long for my amount to double? Yes or no, right? Like, am I okay to wait 9 years for $100 to grow to $200? Maybe not. $1,000 to grow to $2,000. You get the idea, right? So just a quick and easy checkpoint. I think it's fun. And also fun that it works for populations and such. As long as you know the rate. Any questions about that one? Before we do another example.
Where's the 72 come from?
It has to do with the log. So if you pretend, right, that you have, are you sure you,
Okay.
you sure?
Like a brief example.
So if you have n is the log of the future value, right, over the present value, over the log of 1 plus I, right? So if you pretend that the future value is just double the present value, right? And then it has to do with that, the log of 2, 1.5, that kind of thing, right? So here we had the log of 1.5. Anyways, has to do with the logs. Decent. Woo. I think actually the textbook goes through and shows you where it came from exactly, derives it for you. You can just ignore it. Stick to the cool stuff, the easy stuff. I was surprised at how many people missed this one on the test though last term. There's a short answer. How long is it going to take to double? Just the rule of 72, guys. If you've learned anything in this course, I want that to be it. No, probably a little bit more. Okay, moving on to 5.4. So 5.4, we're going to talk about equivalent payments and payment streams again. This is where we get into putting all this stuff together into a huge timeline, right? Big problems that we have to solve, like on the assignment. Okay. So 5.4. Equivalent payments and payment streams. All right. Example 185. I'm not scared. Oof. Okay. Take a deep breath. We're going to tackle this behemoth. Okay. So, Doug's original intention was to settle a financial obligation with 2 payments. Okay. This is always going to be the scenario, right? You meant to pay back this in this amount of time, but you missed the payment and now you're suggesting another timeline. Oh, surprise, surprise. Okay. So Doug's original intention was to settle a financial obligation with 2 payments. Okay. The first payment of $1,500 was due 1 year ago, and the second payment of $2,500 is due 3 years from now. Okay. Doug missed the first payment, of course, and now proposes 3 payments that will be economically equivalent to the 2 original equivalent scheduled payments. Maybe too many equivalents in there. The replacement payments are $1,000 today, a second payment in 1.5 years, and a third payment twice as large as the second in 3 years. What should the second and third payments be if money can earn 8% compounded semi-annually? Yikes. Yeah. So we've got this original payment plan, and then we've got this new payment plan with unknown payment amounts. And I'm very sure that this is the same as, not the same, but similar to assignment 2, question 2. Yeah, it is. So, okay. Let's start with our timeline. Right. Because we've got this kind of original payment stream and then our new proposed payment stream, I'm gonna have them kind of layered on top of each other. Right? Otherwise things get so messy. So I'll start with a blank timeline, and then I'll figure out how many dates I have to deal with. Right? So the original payment plan, and I can just jot them down here, was 1 year ago. I'll erase this after, I guess. I'm just making little notes. Right. 1 year ago, maybe I'll move it up. 1 year ago. Okay. And then a second payment is 3 years from now. Because I have to have like a jumping off point from a year ago and 3 years from now, I'm going to put today on there as well. And then, so now he missed the first payment and he's going to have 3 new payments. So the replacement payments are $1,000 today, which I was going to put on my timeline regardless, right? So that's on there. So today, and then a second payment in 1.5 years, which I don't have yet, so 1.5 years. And then a third payment in 3 years. 3 years is already on there. Nice. Right. So first thing, just kind of weed out what dates you need. Right? So we need 1 year ago, we need today, and then 1.5 years, and then 3 years. So only 4 ticks. After all that, there's only 4 ticks. Yeah. So we've got today, 1 year ago, 1.5 years, and 3 years. I'll also make a note that my rate is 0.08 and my frequency compounded semi-annually, so 2. Just jotting down what they are. All right, now for our payments. So we'll draw the first one, right? The first schedule first, and then the second schedule. So we've got our first payment of $1,500 was due 1 year ago. And then he was going to make a second payment of $2,500 3 years from now. So 3 years. Okay. So we can use any date as our focal date. Remember, the focal date is where we draw all our payments to, right? To make sure that they're equivalent, right? Because we know that he's gonna make a payment today at 1.5 years and at 3 years, right? And so we need to make sure that we draw all these payments to the same date, right? Otherwise, they're not gonna be equivalent. And so, and the whole idea is to make equivalent payments. This payment here at 1.5 years and this payment at 3 years, those are unknown. So we need to solve for those. Right? And so we can pick any focal date. Okay? And like I said on the assignment, I said, solve the problem. Blah, 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 blah. Oh yeah, for question 2, show the complete timeline clearly indicating the date you will use as your focal date. So it doesn't matter what you use, right? Just tell me what you're going to use as your focal date. Okay. So sometimes I tell you which one to use, sometimes I let you choose because it really doesn't matter. Okay. So I'll use 1.5 years. Why not? Doesn't matter. Okay. Why would I pick 1.5 years? 1.5 years is going to have an X, right? So instead of using X as my future value or present value, depending on which way I have to draw the arrow, right? I can just use X, and that's one less thing to worry about, right? But it doesn't matter as long as you tell me what you're going to use. Using 1.5 years as the focal date. So what we need to do, right, if we're going to use 1.5 years as the focal date, then we need to figure out, okay, then what are these payments worth at 1.5 years, right? Because that's what the total of the new payments have to be at 1.5 years, right, for them to be equivalent, right? And so we can figure out, first thing we're going to do is I'm going to pull this guy forward to 1.5 years. Future value 1. So now it's going to be really important that we use the subscripts to denote the order of our calculations, right? Doesn't matter which order we calculate these original payments, right? But we have to add them up before we can keep going, right? So then this guy at 3 years, I'm pulling it back so it becomes a present value. And it's going to be my second calculation. Adding these, right? This is the total original value at 1.5 years. So then I know that the total original value has to be the same as the total new value at 1.5 years. So now I can map out my new payment plan. So my new payment plan is going to be $1,000 today, some unknown amount at 1.5 years, right? So we just denote it by X. And an unknown amount, a third payment twice as large as the second in 3 years. Exactly. So we have 2X there. Okay. So these, right, pulling the $1,000 and the 2X to 1.5 years, right, all these payments get pulled to 1.5 years. Okay. So this $1,000 becomes a future value 3, right? It's going to be my third calculation. 2X becomes my present value 4. Right? And that's why I chose 1.5 years, right? Because then I don't have to do anything with this X, right? I don't have to move it anywhere. So at least that's one of these X's that I don't have to move, right? Also, don't forget about it. If you wanted to use 2X, that's fine too, right? But I also wanted to show you some present values, some future values, right? Anything where the arrow is going forward, we're calculating a future value, right? Anything where the arrow is going backwards, we're calculating a present value. Right? So this is the total new value. Total new value at 1.5 years. Which has to be equal, must be equal to the total original value at 1.5 years. Right? Otherwise, they're not equivalent. All right. So we need to put our ends on these lines, these arrows, right? So n for this first arrow, the length of this first arrow is 1 year and then 1.5 years, right? So it's 2.5 years times the frequency of 2. So n is time times frequency, which is 2.5 years times 2. So my n must be 5 compoundings. This next arrow, n is t times f, which is between 1.5 years and 3 years, I have 1.5 years times 2, which is 3. Between today and 1.5 years from now, I have 1.5 years. Time times the frequency is 1.5 times 2, which is 3 again. And the length of this last arrow is the same as the one above it. Right? So n is time times the frequency, which is 1.5 times 2, which is 3. Okay. Finally, to complete my timeline, I need to find I. Right? So I'll just put it over here on the side. I is R over F. And the rate was 0.08 over 2, which is 0.04. It's the same as before. That's just fluke. But I think we all know that. 8% compounded semi-annually. Ran out of creative juices, I guess. Okay. So here, trying to squeeze it in on one page, this is your complete timeline, right? It's huge, right? But it's showing us exactly what we need to do, right? So once we've mapped this all out, right, we know that, okay, I just have to find my future value, my present value, another future value, another present value, and then I can solve for these unknown amounts, which was the end goal. All right. Let's get to work, shall we? Solve for future value 1. Future value 1 is the present value times 1 plus I to the power of n. The present value is 1,500 times 1 plus I, which is 0.04, to the power of n, which is 5 for this one, but for all the rest of them, it's 3. That's nice, right? We don't have to worry about it. So we're going to do 1.04 to the power of 5. We have 1,500 times 1.216652,902 times 1,500. I get 1824.979354. So my future value is 1824 and 98 cents. Nice. Your future value is always going to be bigger than your present value, right? All right, let's find our present value 2. The future value of present value 2 is 2,500. So find PV2. I'll say solve for FV1 and PV2. Can't do a big header for all of them. Find PV2. PV2 is the future value over 1 plus I to the power of n. The future value we said was 2,500 over 1 plus 0.04 to the power of 3. (1.04 to the power of 3), I get 2,500 divided by 1.124864. That's the last answer that I have on here. So if I just do 2,500 divided by second equals, right, it tells me the last answer that it gave me, right? So I use that trick quite a bit. And then I have to hit equals, and I get 2,222.49 cents. I'll just round to 2 decimal places right away. 2,222 and 49 cents.
Are you okay on the test that we just explained round to the second decimal, or do you want us to?
No, you can just go to 2 decimal places right away. If you're at the end, yeah. So the total value, total original value at 1.5 years is future value 1 plus present value 2, which is going to be future value 1, which is 1824.98 plus 2,222.49. 1824.98 plus 2,222.49. 4,047.47. Nice. So now we know that these unknown payments and $1,000 have to add up to 4,047.47 for them to be equivalent, right? For the 2 payment plans to be equivalent. Okay, so that's why we had to solve these guys first, right? To find what this total is. Now we know what this total must be, and then we can use that to solve for the unknown amounts. Let's find FV3 and PV4. So solve for FV3 and PV4. Future value 3 is the present value times 1 plus I to the power of n. present value of that little guy is $1,000 times 1 plus 0.04 to the power of n, which is 3. 1 plus 0.04 to the power of 3 is still 1,000 times 1.124864 times 1,000. Wouldn't you know it? 1,124 and 86 pennies. Just rounding off right away. So then present value 4 is the future value over 1 plus I to the power of n. The future value of present value 4 is one of these x situations, right? So we have 2x as our future value over 1 plus 0.04 to the power of 3. So I have 2x over 1.124864. 1.04 to the power of 3. Just have it. You want to compress this to just one value times x, right? And so last day, right, we said on our calculator we can use the trick of just using that this is 1 over 1.124864 times 2x over 1, right? Just splitting these two. And then on your screen, right, on screen, you're going to have 1.124864 and then hit the 1 over x button. And you should get that that equals 888996359. Right? Which brings, right, 1 over 1.1248 is 0.88899. So now I can take this times 2 to lump them together, right? And then times x. So you want to use that trick to bring it up top.
Yeah.
Well, I mean, you could just do 2 divided by 1.1248 if you wanted to.
I don't even know what I don't even know.
Like questioning everything I see. No, all I'm trying to do is show you, like, if you get to the end, right, and whether you do 2 divided by 1.12 whatever, or if you say, okay, I'm going to separate these and do 1 over, this is probably the easiest way to do it on your calculator. That's all I'm showing. Right. But whether you want to go 2 divided by this is some number. What I'm doing? Pardon?
No, it's different numbers.
You have to divide it by 2 again. If you do it first.
What?
I did 2 divided by 1.124864, and then I got 1.77 divided by 2 again. And I got that 88.
Because 0.888999 is only this part, right? So then you have to multiply it by 2. But if you just did 2 divided by this, you'll get to the answer right away.
No,
Right.
Oh, I see. That's like the first part. She's right. So you have to multiply that number by 2. I see.
I'm right.
No, I just.
Second time around. No. Here, I'll finish writing it out, and then if you get the same answer, you did it. So it doesn't matter how. Oh. So 0.888 996359 times 2x. Oops. Going over that times 2. I get 1.77799217x.
Then on the test, can I just divide it?
You totally can. I just use the 1/x button on my calculator because I find that's the easiest thing for me to do.
Would it make more sense because you just had a single x, so it's harder to see that? You know what I mean? Like with the 2x, it's easier to see, oh, you just divide 2 by 1. But with
Yeah.
this, it's just x, so it's hard to see what.
Yeah. So pretend you don't have the 2 there. Then like you're saying, it might be easier to just visualize it as 1/. But because we have the 2, right, we're just saying, okay, 2 divided by this, fine, I know how to deal with that. Right? But we do the same thing. There was a question, yeah.
Just leave it in the fraction. 'Cause it's like, if we were doing
Yes.
3/4x, it'd be like that, but. instead
You
just
can.
expressing it.
You can, you can leave it as a fraction, but then you'll have to work with fractions later. So at your own risk. I don't like working with fractions, so I try to get rid of them as quick as I can. Okay.
So if it was like 5x divided by 124, could you just do 5 divided by that number? And you get, oh, so you
Yeah.
just take
Yeah.
one side of-
So all I'm doing here is I'm just showing you how I do it on my calculator, right? Because the whole idea is to be able to keep all my decimals on my calculator, and whatever way you want to do that, it doesn't matter.
So I could just store that number.
Totally. Yeah. Or store your numbers. Screw the 1/x button. See if I care. You can use the second answer key if you want. Wild, right? 2 divided by second answer. Oof. You've got options. You've got options. Okay. Got that sorted out? As long as you get 1.777, maybe less 17, 992,717x. I don't care how you did it. Okay. Or if you're brave and you want to leave it as 2/1.12486, that's okay too. All right. So now we know that the total new value at 1.5 years, I'll write it down here so we've got some room, is going to be, right, looking at our graph here, don't forget about this x. We use this as the focal date so we wouldn't have to deal with that x, right? But now we gotta, right? It's going to be x plus the future value 3 plus present value 4. X plus future value 3 plus present value 4. That's why I gave you assignment 2. So you can practice in the safety of your own home or Starbucks or library, wherever you want. Remember x. Future value 3 was 1124.86. Finally, something we like. 1124.86 plus present value 4 is this 1.777992,717x. Right. So then, right, I have 1x plus 1.8x, or 1.77x, right? I have to add those, collect like terms. Pardon? No, because we're just adding them, right? So this becomes 1124.86, just leaving that doesn't have an x, right? So we can just leave it, plus 2.77799271.7x. Exactly. Right. So we know that the original value has to equal the new value, right? So original value has to equal the new value. Otherwise, they're not equivalent. The original value was what, 40, 47, 47 or something catchy like that? Nice. That's good. Nice. I think it's 7. It was nice and catchy. 47, 47. And then the new value is 1124.86 plus 2.77799271.7x. We might want to store that 2.77 somewhere, right? Maybe I'll store this in 1. So plus 1, store in 1. Because first I need to subtract 1124.86 from both sides. Right? So I have 4047.47 minus 1124.86. I'll show all my work here, just so we don't get lost in the last few steps. Minus 1124.86 is 2.77992717x. Whoosh. This is going to be 2,922.61 is 2.77992717x. I don't mind writing out all these decimal places. I know you guys don't like it, but it's nice to know what you're doing. It's a lot of bang for your buck, right? 2.77, yeah, whatever. Tedious. Now we can finally solve for x, right? X is going to be 2922.61 divided by 2.77992717. So divided by recall 1. Bada bing, bada boom. X is 1052.06. But wait, there's more. Right? We wanted to know what this payment was and what this payment was. Right. So the payment at 1.5 years is 1,052.06, and the payment at 3 years is 2x, which is 2 times 1,052.06. Thanks. Now we're done. Celebrate. You did it. So you do get to practice that again on assignment 2. Fun, right? Question 2. Okay. But I think that's enough for today. That was long enough, right? And the pain and suffering. So if you didn't get assignment 2 or assignment 1, come grab it. Because I've got a lot. Yeah.
So I was working with doing like the like questions,
Nice.
and I was doing like